Alright, so in this video we're going to start chapter 14 on periodic motion. So this entire chapter is going to be involve motion that occurs over and over again, very similar to the dynamic part of lab on Tuesday. So we're going to start by discussing simple harmonic motion. And simple harmonic motion is whenever an oscillation occurs and can be described by a sine or cosine function. And we'll get into more detail of that a little bit later on in the lecture. So we're actually going to start someplace very familiar. We did this in lab on Tuesday, and we also talked about springs earlier in the semester. So we're going to start with Hooke's law. And Hooke's law is our spring force equation. So force of the spring is equal to K times X. So where K is the spring constant, with units of newtons per meter, and X is the distance from equilibrium. Alright, so I have a spring here that I have drawn on the left side of the screen. And we have to imagine that this is one spring that has been pulled back, let go, so it's going to go back towards equilibrium, overshoot and compress, come back to equilibrium, go back out to its original position. So that would be one oscillation. So initially when we pull it back, this is where we're going to get our spring force max. And in a little bit we're going to discuss this. That's how we're putting the energy into the system. So this distance here is X equals A, where A is the amplitude. And this is going to be our max distance from equilibrium. And assuming that we have no friction in our system, A is going to be a constant for the system. You can't get a greater A because that means you put more energy into the system, and you can't have a smaller A because that means you lost energy from the system. So since we're ignoring friction in these problems, there's no way for us to lose energy. Because this is the maximum force, this is also where you're going to see the maximum acceleration of the mass attached to the spring. The spring force is a restoring force, so it's going to pull back towards equilibrium. So this is going to be our equilibrium position. So this is where X equals 0. Now we started out over here, and we use the spring force. We're pulling against the spring force, and then we let go to let the oscillation go. So that means when we're here, we have potential energy, and when we're here, we slowly turn that potential energy into kinetic energy. So that means here we're at rest, and here we're at the maximum velocity. The spring then overshoots, and it's going to go to X equals negative A. So now we've compressed the spring. And this A and this A are going to be the same value based upon conservation of energy. One's just going to be positive versus negative to indicate which side of equilibrium you are on. Alright, so using this information that we've discussed, we're going to derive two equations. The first one is going to be the acceleration of the mass as a function of position. So we're going to sum forces in the x direction, and since we're ignoring friction, the only force acting on the mass is the spring force. So plugging in our equation for force, so force net equals mass times acceleration, and the spring force equals the spring constant times the distance from equilibrium, we can say that acceleration is equal to the spring constant times the distance from equilibrium divided by the mass. So that means if x is equal to a, that's the largest value you can get, and so your maximum acceleration occurs when x equals your amplitude. Alright, so the next equation that we're going to derive is going to be based upon conservation of energy. So as I stated before, when you pull the spring back, you're introducing what your maximum distance from equilibrium is, or what your amplitude is. And that's going to constrain how much energy you have in the system. So initially, you're going to have your maximum potential energy. And that maximum potential energy is going to be based upon what your amplitude is. You're then going to release the spring and let it oscillate. So you're going to have your total energy be some combination of kinetic and potential energy. Now notice I'm using x rather than a here because we've moved and turned some of that initial maximum potential energy partially into kinetic with some potential still left over. So what I'm going to do here is I'm going to equate these two equations. So the first thing I can do is get rid of the 1/2. Now my goal here is to find velocity as a function of position. So I want to solve for the v in this equation. So I'm going to say move the kx squared to the other side. I'm going to factor out a k. And then I'm going to divide both sides by mass. Then I'm going to take the square root of both sides. So this gives us velocity as a function of position, because here's our velocity and here's our position variable.